This is the solution to episode 6, the 100 light bulbs problem. This problem is pretty clearly about numbers, so let's take a moment and see if we can restate things in a more mathematical way. Instead of thinking about players, let's just say we're counting from 1 to 100 and switching every bulb that's a multiple of each of those numbers. The amount of times each bulb is going to be switched then depends on how many factors it has. What we want to know is whether each bulb will end up on or off. This brings up our old friend parity, whether the number of flips is going to be even or odd. If we have an even number of total flips, then that'll leave the light off at the end, since every time it's turned on, there will be a corresponding off flip. Now we have a whole new framing of this problem. The question could be restated as, how many numbers from 1 to 100 have an odd number of factors? Well, factors come in pairs by definition. They're two numbers that can be multiplied to get exactly the light bulb number in question. Does this then mean that the number of factors will always be even, and no bulb will end up being on? Let's go back to the original problem and check our work. We see that the very first bulb is turned on by player 1, and then never flipped again, so clearly it'll end up on, and our reasoning has gone wrong somewhere. What are the factors of 1? Well, they're 1 and 1. The problem here is that there's only one player with each number in line, so repeated factors like this don't count towards our total number of flips. A better framing, then, would be how many numbers from 1 to 100 have an odd number of unique factors. Okay, so we're looking for numbers with repeated factors, where x times x equals y. There's already a math term for this too. When you multiply a number by itself, the number you get is a square. So the first light bulb can be said to stay on because 1 is the first square number. The next light bulb that stays on should be 2 times 2, or 4. Then 3 times 3, or light bulb 9. We only have 100 light bulbs, so the biggest square we're going to get is 10 by 10. The very last bulb is going to stay on. This means that we expect 10 light bulbs in total to be on at the end of the process, every one that has a square number between 0 and 100. Even though this problem had a pretty clearly mathematical setup, it's always fun for me to see how these basic properties of numbers can show up and help us make sense of things in these situations. I hope you've enjoyed thinking through this problem too. Thanks for watching, and be sure to check out this week's new problem, One Switch.